All right, welcome everyone to Sarah's talk on computational thinking. So a little bit about Sarah. So Sarah is the founder and CEO of Tested Minds. Her career spans 17 years in software development in a variety of engineering and hands-on delivery roles. She started teaching computational thinking 4 years ago by introducing her 5-year-old introducing to sort his cards and his toys. She's currently consulting in interim CTO roles, scaling SaaS startups with teams that continuously deliver and flourish doing it. So the same rules apply for this one. Smaller groups. So if you do want to use your green cards and yellow cards, go for it. You can also put them in the chat channel, and we can do questions. So Sarah.
Hi, everybody. Let's just dive in. So what is computational thinking? So computational thinking is a system composed of many components that they interact with each other. And so therefore it's a complex system. And as for many complex systems, when you try to model them after an written language, you're going to lose some essentials. So instead of us just jumping in and give a definition, we're going to go a little bit backwards. We're going to go and talk about what is not computational thinking, and then we'll go through history. So we will find why where we are today is such an important time and place in our lives. And then I'll propose a definition for computational thinking. So this was actually perfect timing because I just gave you the answer. But look, just came in. So I took this picture from one of my favorite series, TV shows called The Brain Games. And the host basically showed this picture to kids who don't know reading, writing, don't know computational thinking, and just asked them which way this bus is going to move if it just starts to move. And these are the kids who don't even know reading, writing. Like, look, who's 3 years old and gave a correct answer. Most of these children immediately came up with a correct answer, while we as adults kind of deal with it, like you have to think. So just, you can think about it for a few seconds, but this actually really depends on where you live. A child who looks at this bus is going to immediately think, okay, I don't see a door on this side, therefore door is on the other side of the bus. And that driver is going to sit on this side of the bus. So for them, they know immediately with one look that this bus, if you're in the US, is going to go to left. And if you're in the UK, it's going to go to right. So things like this that are very, I guess, common sense, you can call it, or things that are we just used to it. These are not exactly computational thinking problems. Hopefully the reason behind it is, I hope somebody sat there and really thought about it. But in our day-to-day things, the things that are used to it or a part of culture, we came to accept it, these things are not really computational thinking. Another thing that is definitely not computational thinking are things that are subjective, so subjective opinions. In this case, this art, it was sold for more than $450 million. Why is that? Can you prove that this art really worth that much? I mean, you can put some price on the materials and the paint and the story behind it maybe, but those are all subjective things, and subjective stuff you cannot prove. So therefore, art or any subjective materials, they're not computational thinking. Another fun example of it that is definitely not computational thinking is when you're doing a mosh pit. So those of you who love doing mosh pits, when you're doing that, you're not thinking computationally. The first time my husband said he used to love these things, I'd scratch my head like, why? Why would you love that? But collective behavior is basically, that's not a good example of computational thinking. Unless you are a physics student, like you are Jesse Silverberg, he used to love going to mosh pits. And in one occasion, he just happened to be looking at mosh pit from way before, like behind. And he had just learned about the collective behavior in his class a week or so before that. So it immediately hit him that, hey, this is actually collective behavior. So he came back home and he started writing the simulator to simulate mosh pit. And he has a fun TED Talk about it, which yeah, I can give you the TED Talk link if you're interested. So again, impulsive impulsive behaviors or decisions, that is not computational thinking. A lot of us also, so I've seen many talks about computational thinking. People say, think like a programmer. And for me, you know, I struggle with this quite a bit because if computational thinking was thinking like a programmer, if you had just hired enough full stack engineers, you wouldn't have any problem solving computational thinking problems, right? It just happens that a lot of times we do hire full stack overflow engineers, you know, and these are engineers instead of, you know, for some of us, instead of really understanding the problem, why is this happening and how could I solve it? We just copy paste it in Google, get to the good old Stack Overflow or whatever is equivalent for, you know, these days, copy paste the solution in the code, get a new problem, and just cycle repeats. So I would argue that computational thinking is not thinking like you can't just say every developer is a computational thinker. They're two different things. So a little bit about myself, you know, I started my journey a long time ago and went through so many different languages. You know, started with Dust, went to C and C++ and Java and Ruby and Clojure and Python. So went on through so many things, but then I realized, you know, chasing the language itself is not going to do me any good. In fact, I'm not that interested. To me, like language is yet another syntax. So I started really understanding or developing interest into what kind of problems are we solving, and then pick up whatever language, whatever technology and architecture fits for that problem. So that was my journey in my career. But then I started thinking about what is computational thinking anyway, when my 5 years old started arguing with me that because mommy is on the computer all day long, he should be sitting on a computer all day long as well. And in fact, he told my employer when they asked him, what does your mom do? He stared in their eyes and said, nothing. So here goes my promotion. But that was just started of this journey for me, that how would I make my kids understand that the computer is more than just a device for games, that you could really, you know, affect their life in the future. And the best way for this was to actually, you know, teach them to be flexible and teach them to expand their horizon, think of different scenarios and be prepared for solving different problems. If you guys are interested, again, for some computational thinking fun, we can definitely talk about that in the break rooms. But so before we go any further, I really love this quote from John Cooking, that he says, life imitates art, and we shape our tools thereafter they shape us. And my take on that is that there is information in the artifact that we produce as a culture, and that information changes us and it changes our culture over time. So going back to the history class, you know, a lot of researchers have dated the origins of Homo sapiens for somewhere around 200,000 years ago in Africa. And for all of that time, but just a fraction, our ancestors had relied on oral communication to pass their knowledge. The fact is we cannot call them illiterate because reading and writing at the time wasn't even invented. But as many oral conversations, like some of you might be familiar with the telephone game, when you say something in the beginning of a line, by the time it gets to the end of the line, it just changes. So when the message changes, there's no truth. There's no objective to truth. So this is extremely important that we realize for such a long time, you know, even if something amazing happened, we don't have objective truth, or, you know, the generations later, they would hear a message that had changed so many times. This is another example. So Walter Ong, he spent his professional career exploring the impact of cultures moving from orality to literacy on their cultures, the impact on their cultures and education. So I'm going to ask this question. You don't have to speak loud, but think about it. If I ask you what item does not belong, which one do you choose? All right. So in his research, he finds out that in oral cultures, concepts are used in a way that it minimizes abstraction, focusing to the greatest extent possible on objects and situations directly known by the speaker. In other words, when he showed this to oral cultures, they said the hammer does not belong, because to them, in their day-to-day life, they see a log and a saw and an axe that they can use to cut the log. Therefore, the hammer does not belong. Versus for many of us, especially those who program, we see a set of tools and a log. So again, like goes back to there is an information in the artifact that we generate, right? And that really changes the way we think about these things. Down to the point that, which item does not belong is completely different for people with oral cultures like oral and those who know reading and writing. And it's a fact that they don't really, oral cultures they don't have abstractions like sets. But yeah, so writing actually restructures your consciousness. So that telephone game and oral culture, it continued for about 150,000 years and plus. And that's the reason we call them prehistoric, because we just don't have any objective truth to learn about them. So somewhere around 6,000 years ago is the first evidence that we see humans writing, and the alphabets actually appeared about 1,000 years even after that. But even when the alphabet exists and reading, writing exists, that didn't mean that a commoner would just see it necessary for them to pick it up and learn that, right? In fact, in many cultures, such as ancient Egypt and medieval Europe, reading and writing was confined to just scribes and religious elites. Why? Because information was power and control, and that's even if the commoner wanted to pick it up and learn, they were confined. They weren't able to do that. But things started changing with the craft literacy. So around mid 15th century, when Johannes Gutenberg invented printing press in Germany, that really changed our lives. With printing revolution, it made it orders of magnitude easier for the knowledge to be captured, to mass produced, to be preserved over time and space. And it also changed that what was printed, who did that, who read that, and what was the thought. That's a very important fact. So to just put this in perspective, I looked at a website called Our World in Data. Between years 1400 to 1800, the population of Earth doubled, roughly about doubled. What happened to books? We actually, during those 4 centuries, we went to close to zero to about 1 billion printed book. So what impact it had on our culture, you can see on many countries. So this is actually just on Europe, and there's some anomalies you see, but you see in many countries, actually, the people who know how to read and write, it actually doubled or tripled. So this is extremely important because this was now our transition. Printing press was our transition from those Middle Ages and Dark Ages to the life that we have been living. This is another quote from Marshall McLuhan. In this quote, he's actually talking about media, in fact, writing in Greek culture. But in the same way, printing made literature possible. It didn't just merely encode it. And it's again, like it's important to know that before printing press, books like this were unheard of. So this is a trigonometric function written in 1619. So around craft literacy time, before everybody was able to read and write, books like this were just unheard of, and they were very error prone to write. Who would write? It's scribes or religious leaders who were not qualified to have these books. So Matthias Berninger, he was a child growing up in Protestant Reformation area during the after the printing press, and he actually wrote this book that could be used by astronomers and navigators and building architects. So this is one example that the printing press actually made this happen. This is another example that I really like. This is Betty Stafford. She's on the left. And she was recruited during World War II. People like her were recruited from PhD programs to come and work for companies that were earlier version of NASA. And they were praised for getting so much done during one morning than an aerospace engineer could have done, could have finished in a day. So what you're seeing on the right side of the screen is Betty's thoughts. She's actually working on converting a log 10 of a number from a more modern equivalent book of Berninger's to a natural log. But again, reading and writing and printing press had enabled her to document her thoughts and therefore pass that knowledge to other people and preserve that knowledge. So this is absolutely important. Of course, she had some calculators and stuff to run calculations, but most of these thoughts, most of these calculations were in her head. So another thing that happened during World War II, it funded massive amounts of R&D into human and mechanical computing to solve problems for the H-bomb control, right? But what happened here, without getting into too much detail about it, these people, the women who were, by the way, first computers or engineers, not only they had to have very detailed information about the problem, but they had to come up with the solution, and they had to engineer this ENIAC to actually rewire the cables and be able to run their code to see if the solution works. So in addition to the problem knowledge, that the knowledge they had to have about the problem and the solution, they had to also learn detailed engineering of the computer to be able to program it and run their ideas. And what happens if they had a mistake? Sometimes those mistakes would cost a week for them to just go back and reprogram everything, come back and test their ideas. So what we really needed was a good abstract to enable these people to focus on what matters and not so much about things that could be solved otherwise, right? So like deep down engineering of the computer. This is a good example I found. So this shows basically that when the picture is too detailed and too realistic, it's very distractive, right? So in the same way, if you have to run a code or do something and you're so into learning every single detail of every library and everything, that will distract you from what you're supposed to do. And on the other side, if it's too abstract, if you're just copy pasting and not learning anything, again, like that makes you just a power user. So how much abstraction is really needed? Pragmatic Dave Thomas, he actually said that you don't need to stop when you have a perfect model. You stop when you reach an imperfect model that you understand. So same way when you're learning a new technology or anything, you just need to really open suitcase and libraries enough for you to really understand, enable you to do your job. So what happened was around 1945, von Neumann architecture, now it gives us a stored program that we don't need to rewire the machines anymore in order to write some code and test things. With this, our thoughts, concepts becomes codes, and the code is now data that we can automatically execute it by the machine and get fast feedback. So what does that mean is, in this example, Betty's writing on the left side, you can see that she was perhaps like learning something about downwash. So she documents all her thoughts and calculations, and perhaps had to send this out to test labs to be built and get tested for her to get some feedback and reiterate on that. what you see on the right side was Dr. Lorena Barb. She opened up Jupyter Notebook, wrote a few lines of code, and immediately was able to run that and get fast feedback about how her ideas and calculations are going to act, or how it's going to look. So again, the concept became code, and the code is what we use to execute. So I went through history to get to this point that we went from orality to printing press that had that huge impact with literacy. And I would argue that the age that we live in right now, with all these programming languages and the computers, are the age of computability. So this is going to have another very big shift in our culture, in our lives. We are amongst the first generations in the history that are able to interactively explore our ideas on a machine that it can execute it with no subjective judgment. And that's extremely important, and no permission required, unless you want to do sudo, but really no permission required. And the computer doesn't judge you on the code that you're writing. And that is going to make our ideas falsifiable and tangible. So we have an object that we can really think with. And most computers these days, it's not even that expensive. Time is an essence, but when you think of the time that you're going to lose later on things that you did not test, you did not run, you realize that testing is actually cheap in a good way. So all models are wrong, but some are useful, as we just discussed. So if I were to have a definition for computational thinking, I would say computational thinking is an iterative system of generative reasoning in which people build models of subjects in a notation capable of being executed objectively and automatically by a machine with observable and falsifiable output. And that's the longest sentence probably I have written. So as Brian Merrick says, an example would be pretty handy right now. So let's just jump through a couple. So I try to bring some examples that always fits the audience, but of course, feel free to jump in, especially during break if you have other examples. So some of you might have heard of this. This is the Mars Climate Orbiter. So what happened in this example was it was a robotic space probe that it was launched by NASA in December 1998 to study atmosphere and climate around the Mars. So on September 23rd, 1999, a little over 9 months later, communication with this aircraft was lost. Prior to the loss, the navigation team had detected that the altitude might be much lower than it intended to be. So 24 hours before the orbit insertion, a calculation went into place that would hopefully fix and survive. This aircraft could survive. What happened was the spacecraft started the orbitation, the insertion maneuver, and as it was planned, but it was 49 seconds earlier than expected. What was the bug? What happened? We actually lost, and we don't know what happened to the spacecraft. It might have inserted and crashed, or it might have diverted and gone back to space. What happened was, in the US, we are using United States customer unit. The rest of the world uses metric system. So when people came up with this solution, the engineers actually calculated or wrote something in metric system, but we needed an imperial system. So there was no test happening there. So that one small test that was skipped during, this is important, let's launch it, actually cost us about $327.6 million. And I have seen this over and over again. Like, this is, of course, like, it's a big example, but I have seen this over and over again, that a lot of people that say, we're in a rush, don't spend time in testing, let's just push it, I know it's going to work. So who is here to blame? Is it the engineer? Is it the person who actually clicked the button? Is it the person who might have forgotten to read, the acceptance criteria, or was it even? So that's just a good example of how monkey patching doesn't always work. Never skip testing, especially when you talk about integration with two systems. Always be suspicious. If it might break, it is going to break. Another example here that really shocked me was regarding to a lady called, her name was Karen Sandler. So Karen suffers from a big heart. So there's a condition. I'm going to try to pronounce it. Excuse me, I'm not a medical profession, but it's called the hypertrophic cardiomyopathy, or in short, HCM, which your heart is actually getting enlarged and thick. So this patient was wearing a device, a defibrillator or a pacemaker, to help her in the event of sudden death. That could, the device could help her heart and she could come back. But who would have thought a woman could get pregnant? So Karen was pregnant, and this device was never tested on pregnant women. So what happened, this lifesaver actually shocked her twice during her pregnancy. And luckily, she is fine. The baby is fine. But that just tells you that diversifying the example, especially when it comes to these things that are literally a matter of life and death, is extremely important. I'm going to go a little bit faster. I know we're short in time, but just to make sure, again, like these computational thinking that went through your head, how are you going to pass that knowledge to the people who come to your team? How I would say a good code, a good architecture is when a new member joins a team and they're able to get their environment up and running and they have their first PR pushed by the end of the day. How are you going to make that happen? How are you going to capture that information? One solution that's actually, I love this, is ADRs. So with ADRs, you can actually record your architecture decisions there, any conversation that happened, any options that was there, so that the next person who comes in and have questions, they can always go back and actually recreate all the thoughts and discussion that went through your head when you came up with a specific architecture or a solution to make. This is a quote from Joseph Blake, and basically he does emphasize that the why of the ADR combined with how of infrastructure as a code in their case has made such a great transfer of knowledge for their teams, and of course for onboarding new members as well. So to wrap it up really quick, again, computational thinking can and should be the system thinking. Where there is a code, where is your code going to be running? Who are the people who are going to use that software? And when the impact of failure is high, we have an ethical obligation to object to doing shoddy work. People are paying us they may not understand because that's a product and they're excited about it, but we are the last line of defense. We are the one who are writing that code. And it's our duty to really fight for it if we're not comfortable or is against our ethics to build the software. This is, I had to put some animations here, so bear with me. Again, it's very important to diversify your test samples. I had this quote from Michelle actually early on, that when it comes to people, there is no average, and that's extremely important. Prioritize the rare cases, in cases that even small mistake could ruin something. We can't always prevent all the bugs. That's just not going to happen. But having a good system to be able to notify the teams when those bugs happen and what to do and who is going to be a responsible person to take care of it is a must-have in every good software, I would argue. And simulate the word behavior, then update your simulations, learn from your word, and go back and change those again. So it's always fast feedback. These days, it's cheap. Just build it, get the feedback and be open-minded about being wrong or about modifying anything that you're building. Systematic problems are most likely going to happen at the interface between the components. So integration testing is must, even though a lot of projects were just overlooking that and missing those. Last but not least, the code is not computational thinking. Your tests, your simulations, your documentations, all of those should help recreate that computational thinking that went through your head, and the design for people who are going to join the team later. So I'll leave you with that. But yeah, chime in. I hope that, at least all these bold stuff on the screen makes sense. If not, let's just have a discussions and talk about what you guys are thinking and your experience.
All right, thanks, Sarah. So let's see, do we have any questions, green cards? You can put it in Slack, or you can put it in, you can hold them up and I'll try and see your face. All right, let's start with Eric.
I think that what I heard here was kind of thinking the way people who work with computers do. Do you think that there's maybe some, you're talking about like a common way of approaching problem solving that people in our industry are likely to align around?
If I understand your question, so yes, so it's the message is, we have a device that we can think with, and we really need to put this device into use, especially when it comes to building software, or even answering anything. Right now, especially with the current situations, for example, that's one example. There are a lot of questions, a lot of ideas about the life we're living with, right? And we're in the age that these days we get so much data. We're not yet there to really understand how to use that data, but the more data we have, we can run those simulations with a computer and really see the effects. So build a model, run tests, and really test our ideas with just writing as simple as like opening up a Jupyter notebook. And especially again, like these days, a lot of people are learning to program, right? Some of us are going deeper, we become programmers, we become testers. Other people are actually power users, and that is okay, as long as they understand that they can still open up something like Jupyter Notebook, super simple, to test some of those ideas. And does that answer your questions? Or?
I'm going to go with yes, that answered Eric's question.
Yeah.
No? All right. Okay.
No. Well, yeah, we can definitely talk.
Since I haven't seen a flurry of other cards or anything, I'm thinking that we have a lot of creative work in the kind of stuff that we do, and a lot of coming up with new ideas. I think that the way you're talking, what you're talking about here as a way to approach reasoning problems, as a way to think through things, I think is actually super powerful. Especially in testing, where we get people who might not have had a CS background or anything like that, and some of these approaches are pretty new. But I mean, I picked your talk, so clearly I like what it says anyway.
Thank you. Roxanne?
Roxanne, yeah.
Kind of unmute. So I think my takeaway from this, and I mean, it's biased because of things that have been going on like within my organization, but since there's so many of us, like, so obviously all of our developers, but our test group is now limited to mostly test engineers, so mostly focused on automation. And I think is in a lot of the industry, maybe not the testers don't feel this way, but the corporate people feel that manual testing can sort of be pushed aside. We'll just do more automation. And I think that when you have a bunch of people who think computationally, which would be developers and automated testers, you definitely have to maybe reach out more often in order to get feedback or sort of the creative side. And like the first thing that comes to mind is I notice a big difference between the way developers think and the way like our UX people think. So I could like going to my UX people and saying, you know, how would you use, how does this look to you? Even though they give us the design, like getting information from them as an actual user might be helpful, because otherwise we're kind of biased to that computational thinking. You know what I mean? So that's
absolutely. Yeah, and the takeaway is that it's not like I mentioned, programmers are not all computational thinkers, right? Actually, the people, like the fact that you can go back and, like I mentioned in one of the slides, observe how your software is getting used in the world. You know, have your testers, diversify your testers, and then get that feedback from them and build it again and put it in front of them again to be able to test it. So that's one message that I really want to get across. That again, like I had some slides that I had to take out, that not always. It's a fact computer makes things easier, much easier, much faster. Those calculations that sometimes takes days in our head, you can run within like few seconds on the computer and get answers. So when we have it, we have to use that. If that means that, yes, engineers build something, and I always say that actually, as an engineer who always day in, day out, write the code and look at the code and work with test samples, I get blind to some issues and some stuff. So it's always, I always actually argue to have automation, but also always have manual testers. And not only that, I'm very much pro of going to really users, like even a few of my previous projects, just go to university, show the kids their app and just tell them to use it, and really sit there quietly and observe how are they going to use it. Where is their eye moving? Where is their thumb or fingers moving on the app? So those are all the feedback that we can come back with all of that information and build something again to get tested. The other thing is, in subject of even children, for me, the one thing that I wanted to get across, especially with my kids, I'm biased, I don't want them to be on the computer all day long, was, hey, if you can do your bucket sorting and bubble sorting with hand, then when it gets to 1,000, you can use my computer. I teach you how to program. So one way of me, for example, teaching all of those to my kids was, hey, here's a basket of laundry, have your imaginary buckets and sort this. And that's called the bucket sorting. So getting them introduced that, hey, you don't have to always have a computer to test your ideas. It's just that this machine is going to make that feedback loop much quicker, much shorter when you can use that.
Or Sarah, that's just a sneaky way to get the kids to separate your laundry.
I did actually.
Good job.
Yeah, yeah. My older son thought that if he bubble sorts, he can go and hit a jackpot. He was asking me how much money he can learn if he learns bubble sorting. It's like, yeah, probably nothing, kiddo, but it's still a good skill to have.
I don't know about that. I mean, you see what an entry-level engineer gets.
All right. James had the next green card. So James.
Yeah, thanks, Chris. I was wondering how important the falsifiable output part of your definition is. And I guess I was thinking that you might use computational thinking to build a machine learning model, which can clearly be objectively and automatically executed, and the output can be observed, but it's not necessarily easily falsifiable.
Not easily. You're absolutely right. Especially when you think about like smarter software that you can teach the computer to do something, that actually bakes into the ethics for me, right? You want to make sure you're very, again, as being the last line of defense, when we're building those softwares and machine learning, we also have to think about what we're actually teaching the computer to do. But the bottom line is, if you have a line of data, right, and run that by a computer, by just an algorithm, that algorithm is not going to really give you the answer you want to hear. It will run those algorithms on the data you have, and if you're as neutral as it could get, you could really explore if your idea was right or it was wrong. But you're absolutely right in a way that it could not always, like if we're thinking about like especially programs that more into teaching the computers what to do, we have to be super careful on what we put in.
So is falsifiable crucial to this definition or not?
I would say still is crucial because again, the computer itself, it runs the data. So for me, it's important that if I can prove my idea right with one set of data, it should be probably proven wrong with a different set of data or things that I don't want to, right? Or things that I might assume. So that is, to me, it's still pretty important.
Okay, I guess I don't really understand why it's important because the computational thinking looks to be a way of building a model, and in your definition you've got that the model has to be in a particular kind of form that it can be executed. But if the thinking is to get to the model in a particular form, why does the observability and falsifiability matter at all?
What would happen? So if you're trying to prove something is right in like in a specific format, right? How are you going to prove that it could break if a data changes or something changes? Like, it's like open discussion. So anybody please jump in. Like I put this together, but I'm also very interested in hearing all the feedback.
Well, I mean, that's the testing job, looking for ways to try and find problems. But, the kind of space of all possible outputs is usually pretty large in any kind of, realistic piece of software. So you can't necessarily guarantee to find or prove, as you put it, that the program works, because there's always another case where it might not work. You can't test them all.
You can't test them all. That's absolutely correct.
So that's why, I guess that's why I'm wondering why the falsifiable part is so important. Or I might just be completely missing your point, so forgive me if that's the case.
No, that's definitely fine. Again, like from the reason I put in was just so that, for me, it's important that it's important that I can prove myself right or wrong. And that's something that I think when you run like quantity data, a large amount of data, without a computer, you might become biased or you might miss some stuff, right? But when you run those large amount of data on a computer, the computer should be able to find those anomalies and should either prove you right or wrong. So that's the reason, that's what went through my head when I put actually the falsifiable also included in this paragraph.
Okay, thank you.
Any additional green cards, either visually or in the chat channel? Otherwise, I think we're at time right now.
I think we have one.
Oh, we do. Okay, Alari.
I'm sorry. Yeah.
Go ahead.
Yeah, so Sarah, thanks a lot for your session, which was absolutely fascinating to listen to. So your sentence that you have here on the screen, I find this incredibly fascinating because it just draws my attention to it, and it almost seems to be like a Zen Buddhistic koan to me, in some sense. And it's I probably just have to. I actually took a screenshot to reason on it maybe later on, but it's whereas James has been focusing on the later part, my interest is in the first part. So you've got this computational thinking as an iterative system of generative reasoning. So to me, computational is one property that machine does, whereas thinking is very a human-centric property. And the same thing, generative is a property that machines do, and reasoning is a human property. Could you expand a little bit on the connection between these two things? And this really goes into the center of what I'm deeply interested in the interplay between human and machines. which basically is the focal point of software testing is kind of these interplay in a systemic level where machines and human interact. And there is such a density of these combinations in just the first part of your definition here.
Yeah, sure. So what I was thinking, so I went through so many iterations of how can I just like summarize all the stuff that to me is important about the computer, right? At the end of the day, again, like when it comes to what computer can do, if we take time and space out of the equation, are things that our human mind should be able to do, right? So whether it's fast calculations, long calculations, processing data, and all of that. But when you think about our human mind, we just don't have that capacity. We're very, very error prone, versus computers are not. Computers are much faster. They can do calculations in seconds that could take us hours and days. So that is what goes to my head. That kind of marries that computational thinking, something that why computers are so important in our life, and the human mind. And of course, when it comes to, again, iterative system, generative reasoning, those are the things that the fast feedback that you can get from the computer. Like you have an idea, it's going to take me days to calculate and to run simulators. Let me have a program, let me run that with the computer and get really fast feedback with it to prove myself right or wrong, or learn something about it and build on that feedback and test it again. So that's, I think, one of the most powerful attributes of computers, and in how our culture and our life is going to be shaped, hopefully.